Hello class, I'm so glad you're watching this video. We will not cover all the organic chemistry too here. We will skip radical reactions, reactions of conjugated dienes, including Diels-Alder, and we will skip aromatic reactions. But the rest we will try to cover, and that includes organometallic reagents and also reactions of carbonyl derivatives. First slide is about carbanion containing compounds. So R- comes in two flavors. You can have Gilman as a source of R- and Grignard reagent as a source of R-. First things first, how do you prepare both? How do you make Gilman and how do you make Grignard? Stop the video and think. Yes, to make the Gilman reagent, take our organohalide Rx, add some lithium followed by copper iodide. To make Grignard reagent, take organohalide and throw some magnesium metal. Now, even though both of them are a source of a carbanion of R-, they have different reactivity. Gilman reagents, they love to replace halogen for the R, and they like to do Michael addition. Grignard reagents, they love to attack carbonyl groups and other polar groups such as nitriles. Stop the video and predict. What do the products of these reactions look like? Yes, so Gilman just swaps the halogen for the R, very useful reagent. And Michael addition means it doesn't attack the carbonyl, it attacks the beta carbon. So if this is your carbonyl, this is the alpha, this is the beta. So R- attacks the beta to form an enolate. By the way, this Michael addition process, not just Gilman reagents do it, but a lot of other stabilized anions do a similar process. In fact, when you see an enone, try not to forget about this useful process. Grignards are a lot more straightforward. When they see these carbonyl, nitrile, Grignard loves carbonyls and it nucleophilically adds to it. And you can see how here it attacked the carbonyl, the pi bond breaks, attacked the carbonyl, the pi bond breaks, attacked the nitrile, the pi bond breaks. These are not the final compounds usually. Once you have those oxygen minus, nitrogen minus compounds, you add some H plus, HCl or H3O plus. And of course this will become an alcohol, OH. This will become a carboxylic acid, OH. At first you make NH, but these are not stable. So eventually this third product, this imine, will get hydrolyzed to a ketone. So adding Grignard to a ketone makes an alcohol. Adding Grignard to dry ice, carbon dioxide, makes carboxylic acid. And adding Grignard to a nitrile eventually makes a ketone. This slide shows how to introduce a nitrogen atom into the molecule. You will see that all of these reactions are SN2. Identify a nucleophile and a leaving group, which is clearly bromide here, not hindered, so nucleophiles easily replace it. Pause the video to draw the products. See how nitrogen, the lone pair, replaces the bromide, loses a proton to become neutral amine. Cyanide replaces the bromide, you make a nitrile. Azide replaces the bromide, you make this propylazide. Nitrite replaces the bromide, you make a nitro derivative. And then this phthalimide, you make this phthalimide derivative. Now, what are these products useful for? Take the time to think about how the following reagents modify these functional groups. The first three are reducing conditions. They bring hydrogens into the molecule. So the nitrile gets reduced to a CH2 and H2 group. Oh, we have a primary amine in the end. A Z gets reduced to primary amine. Nitrogen gas flies off, N2, and you have the other nitrogen filled with hydrogens. And then nitro group gets reduced to amino group. Finally, the last set of conditions, you actually have this amide, sort of like a protecting group on this amine. And you can either use acidic hydrolysis, H3O+, or basic hydrolysis using something like sodium hydroxide, or a milder set of conditions using hydrazine, N2H4, to cleave this protecting group and make a primary amine again. This last last sequence is called Gabriel's synthesis of primary amines. Look how all of these methods complement one another, and they allow you to convert a bromide into an amino group. This slide is about reactivity of ketones and aldehydes. Draw what do nucleophiles and bases do to ketones and aldehydes. Nucleophile adds to a carbonyl group, attacks the carbonyl, pi bond breaks, and usually this is followed by H plus addition. H3O plus or HCl acidifies it. O minus gets that proton. Now, which groups react in that way? Think about it. Lithium aluminum hydride, LAH, sodium borohydride reduces ketones also. Grignards provide carbanions as nucleophiles, also enolates and enamines. And we will talk about those just a bit later, but they also are nucleophilic and they add to ketones and aldehydes. Bases, they deprotonate, and they specifically deprotonate the hydrogens next to a carbonyl group because the resulting species, enolates, are stable because of resonance. Now these enolates are nucleophiles themselves, so they might attack another ketone or aldehyde if it's present in the mixture. Or they might attack methyl iodide and replace the iodide in methyl iodide. They might attack bromine, Br2, and this allows you to build a carbon-bromine bond. Another example of a nucleophile is this carbanion, which is linked to a positively charged phosphorus. Now these are called ylids. If you recall, ylids react with ketones and aldehydes in what is known as a Wittig reaction, and this allows you to make alkenes. Now, under acidic conditions, what happens when ketones and aldehydes react with an alcohol under acidic conditions? And that can actually happen once, or then it can continue reacting, or with bromine under acidic conditions. Well, hemiacetal results. By the way, how does it happen? Proton activates the carbonyl group and then alcohol attacks that carbon. So you have hemiacetal after loss of a proton, and then it can continue reacting. So the OH can get protonated, leaves, alcohol attacks again. You have an acetal, this molecule over here. Why are these useful? Well, they can be used as protecting groups for the ketone. And there's a way to bring them back to the ketone or aldehyde. You can either do acidic hydrolysis, and acetal can only be cleaved under acidic hydrolysis. Hemiacetal can be cleaved under acidic hydrolysis, but also under basic hydrolysis because the base can deprotonate this hydroxyl group, and that will kick off the alkoxide. Bromination under acidic conditions results in adding bromine to the alpha carbon of the carbonyl group. How does this happen? This happens through an intermediate formation of an enol. So catalytic H plus causes tautomerization to happen, and then enol reacts with bromine, and the resulting molecule rearranges to make this bromo alpha ketone. The next half of this slide is dedicated to reaction of ketones or aldehydes with amines. So what will happen when ketones or aldehydes react with secondary amines or primary amines? Pause the video and think about it. Imine cations or imines result. If nothing else is present in the mixture, iminium cations become enamines. And if there is an additive that provides a source of H-, this is called sodium cyanoborohydride or sodium triacetoxyborohydride. So those are very mild sources of H-. They are so mild that they don't react with ketones or aldehydes. They wait until iminium cation is formed, and only then they attack it to form amines. The overall process in this case is called reductive amination. Amines are nucleophilic with their nitrogen. Why are enamines useful? It's because they are nucleophilic at their carbon. So through a resonance structure, you can see how this carbon over here is a nucleophile. For amines, there are two useful transformations that we've learned. Predict Cope and Hofmann elimination products. Yes, so Cope is when you oxidize an amine into an amine oxide, and then you heat it, and this O- deprotonates a proton on this carbon right here, so that a double bond can be formed while this nitrogen derivative leaves as a leaving group. For Hofmann, you need to make a quaternary ammonium salt, so you will react it with methyl iodide as much as you can, while this trimethylamine piece is a good leaving group. So then you use a base, and traditionally people use wet silver oxide, and that is a source of OH- that causes deprotonation in this position. The leaving group leaves, and you essentially form the same alkene. Before moving to carboxylic acid derivatives, it is worth stating that amines, enamines, iminium cations, all of them can be easily hydrolyzed under acidic conditions back to ketones and aldehydes. And amines, of course, if you are to react them with an acid, they just get protonated. Esters, chlorides and anhydrides, nitriles. There's a lot of similarities between them. What will happen when nucleophiles react with these polar groups? Think also right away which particular nucleophiles you've seen react with these groups, and what happens when they react twice. With esters, while nucleophile attacks the carbonyl, the pi bond breaks, comes back, alkoxide leaves, you form a ketone at first. Some nucleophiles react again, second time. Which nucleophiles react twice and which nucleophiles react once? Well, LAH reacts twice, H- in the end will add twice and you will have a primary alcohol. Also Grignard reagents react twice with esters, so you will have a tertiary alcohol. What reacts only once? A specially designed reagent called dibel. Dibel at low temperature adds just once to an ester and it allows you to isolate an aldehyde. Amines react just once to make amides. Alkoxide react just once to make transesterification reaction. OH- reacts just once to cause hydrolysis and form carboxylic acid. Enolates react once, that would be Claisen condensation, and enamines react just once. With acid chlorides and anhydrides, same idea. In fact, even less reactive nucleophiles will react with acid chlorides and anhydrides, and the reaction will happen faster because the chloride is much better leaving group than an alkoxide, and then many nucleophiles will choose to react again to form a similar looking product. Which nucleophiles react twice? Well, LAH and Grignard reacts twice, very reactive. Even sodium borohydride now will react twice with acid chlorides. It takes a much less active nucleophile to react once. We call this reagent drunk LAH, so it's lithium aluminum H and then 3 terbutoxides. That allows you to make an aldehyde from an acid chloride. Amines without any additional activation add to acid chloride, chloride leaves, and you form amides. Alcohols react once, water reacts once, enolates and enamines, they all follow this reactivity. What happens when a nucleophile adds to a nitrile group? Well, it attacks the carbon, the triple bond breaks, and you generate this anion. This can react again with LAH. This happens second time, and then the N with two minuses gets protonated to make an amine in this case. Many more nucleophiles add just once to a nitrile. So what reacts just once? Dibal, Grignard, OH-, they add just once to a nitrile. What happens when bases react with these groups? What do bases do? Deprotonate. So you get an enolate here, which is capable of attacking, for example, other carbonyl derivatives. That will be Claisen condensation or aldol condensation, depending on what it attacks. Or it can react with bromine, or it can react with methyl bromide as a nucleophile. What will a base do to a nitrile? Deprotonate and make this stabilized anion. We haven't talked much in our course about it, but reactivity of this anion is about the same as it is for this deprotonated ester. What happens when acids react with these groups? It's a typo on these slides. Instead of H+, imagine it's H3O+, so it should be written H3O+ for both. What will be the product? So H+ activates the carbonyl, and then water attacks the activated carbonyl, results in proton shift, loss of alcohol, and as a final product, you get acid. So H3O+ allows you to hydrolyze an ester into an acid. Lewis acid takes halogen away from acid chloride, makes this acylium cation, and this is a key component of a Friedel-Crafts acylation. So when it sees the benzene ring, and I know we need to jump back into aromatic reactions, but it does electrophilic aromatic substitution and results in adding onto the benzene ring. Now when H+ activates the nitrile and then water adds to the activated nitrile, after all the rearrangements, you get amide. If we want to bring back amide to a nitrile, we need a reagent that can suck water, H2O, away from this molecule. So these reagents are thionyl chloride and phosphorus oxide, P2O5. So either one of them will be enough to convert an amide back into the nitrile. Now what can we do to an amide? We can continue reacting it with H3O+ conditions. Think of what will happen here. React it with LAH or hydrolyze it under basic conditions. Spend time to think, what are these products here? Okay. Acidic hydrolysis hydrolyzes amide into carboxylic acid, so splits this bond, protonates the carbonyl, then water attacks the carbonyl, then nitrogen leaves, and you form an acid. LAH, that's a rare reaction, but it causes reduction of an amide into primary amine. Then hydroxyl, of course, hydrolyzes it into an acid. The product is just the same as when you use H3O+ conditions. Last major functional group, carboxylic acid. Pause and spend time to predict products with all of these reactions that carboxylic acids engage in. The first path is very, very rare because most nucleophiles are basic. Most of them will go this route over here. But if you use LAH, not only deprotonates first, but it's still active enough to attack it as a nucleophile, and the reaction happens twice. So LAH reduces acids all the way to primary alcohols. Also, organolithium compounds not only deprotonate over here, but then they keep adding twice and result in tertiary alcohols. That's a rare process, though. I think most of the time you mostly see it with LAH, reacting with acids twice. Now, bases deprotonate acids. Rather than deprotonating it next to the carbonyl from a carbon, they deprotonate the oxygen because you form a stable carboxylate. An interesting reaction is with CH2N2, that's diazomethane. So CH2 here has a negative charge, which means it's a base. It deprotonates the acid, and then the O- replaces the nitrogen, and that results in formation of a methyl ester. So this reagent is a very nice way to convert an acid into a methyl ester. Now, if you mix acid and alcohol under acidic catalysis, that's Fischer esterification. It allows you to couple both reagents and form an ester. Thionyl chloride, many of you remember, converts an acid into an acid chloride. Now, some of you remember this reaction that's called Hell-Volhert-Zielinski reaction. And it converts an acid into an alpha-bromo acid. The mechanism is quite complex, but whenever you see phosphorus tribromide and bromine, it adds bromine onto the alpha position of a carboxylic acid group. That's it. So it reacts in 6 different ways. Now, a couple of reactions were too difficult to cram into the previous slides, so I put them into a separate slide. This is what we call UNO reactions, something that is hard to spot. Whenever you see this substrate produced or this substrate produced, they are not stable. What happens to them the moment they are generated? Try to draw. Yes, the first one is a dehydration. This system very easily loses water to make enone, and that's usually the last step in the aldol condensation reaction. The second reaction, the UNO number 2, is common for all carboxylic acids that have a carbonyl group in the beta position. Those are not stable and they lose carbon dioxide and they form a carbonyl compound. That is very useful in malonic ester synthesis or acetoacetic ester synthesis. Last but not least are a couple of oxidants. If you want to oxidize an alcohol into a ketone, take PCC or chromium trioxide. But if you are dealing with primary alcohols, you need to be careful. So one of these reagents is a lot harsher than the other. Which one will oxidize it to the aldehyde and which one will oxidize it all the way to a carboxylic acid? PCC is the mild one. It's good enough to oxidize into an aldehyde, but it will not convert aldehyde into an acid. While chromium trioxide is definitely harsh, so it will convert an aldehyde to an acid. Same, you can begin with the primary alcohol, converts it into all the way into an acid. There's also a mild reagent called Tollens reagent. Silver oxide with ammonia converts an aldehyde mildly into a carboxylic acid. So it's good to know these choices over here. Thank you for watching. Advice is not to cram all these reactions, but to see patterns. See how pretty much all reagents fall into different categories: bases, steal protons, nucleophiles, add to carbonyl groups, acids, protonate. Try to see commonalities between the transformations. Then try to spot the differences too. For example, LAH reacts twice whenever it can. It is so reactive, but dibal is not as active. It reacts only once to reduce esters and nitriles to aldehydes. And when you see a transformation, limit all the hundreds of options to a specific functional group. Don't think, for example, that 100 things can happen to a nitrile. No. By looking on the slide about nitriles, try to realize that only 3 things can happen to a nitrile. You got this, people. Best wishes on your studies.